So this is the second video with more examples of using ideal gas law and Dalton's law. And if you are watching this, then you'll get some different perspectives and some more examples that were not required. If you need help, this is a great place to come for help. So the first thing that I want to look at now is some different questions. And remember that when we look at a gas laws question, that we have to decide if it's a before and after comparison type question or if it's a single point in time question. So we have a rigid plastic container that has 35 grams of gas at a pressure. And grams, remember, is not one of our variables, but grams could be converted to moles, right? Which would be N at that point. We have a pressure, and we want to know what is the pressure if 5 grams are removed. Okay, so we'll have to figure out how much is left in the container, but we can figure that out. So this is a before and after scenario, and it looks as though we're using pressure and moles. So this would be P1 V1 over N1 T1 equals P2 V2 over N2 T2. And they're saying the temperature is constant, so we know we can ignore the temperature, and they're saying it's a rigid container, so we know the volume doesn't change. So this would be P1 over N1 equals P2 over N2, which means we need to convert our grams to moles. So we can come in here and say 35 grams of C2H4, grams of C2H4, 2 moles of C2H4, 1 mole, and from the periodic table, C2H4 has a molar mass of 28.06 grams. So we started out with basically 1.25 moles in our, of ethylene gas in our container. And then when we're finished, we removed 5 grams. So that would be 35 grams minus 5 grams equals 30 grams left of C2H4. And it's the same molar mass and 1 mole. And this comes out to 1.07 moles. So now we can substitute in our formula. Over here we have a pressure of 793 torr. And when that was the case, there were 1.25 moles in the container. And we're looking for a new pressure, and now there are 1.07 moles in the container. So I can solve for P2 and see that this would be 679, I'm going to keep 3 sig figs, 679 torr of pressure. Or I'll show you the new way again. Remember that if we're looking for pressure, we're going to start with the pressure we were given. So that would be 793 torr. We're going to multiply by a fraction here. The relationship is between number of moles and pressure, and number of moles has decreased. And remember that the fewer moles you have, the fewer collisions there are, so the pressure would also decrease. This means our larger number of moles needs to go in the denominator so that the pressure goes down. So this would be 1.25 moles in the denominator and 1.07 moles in the numerator, and I'm going to get the same exact answer. So there's another example that shows you both of those ways to do that with a little bit of a twist. So let's come back and do another one that uses the density formula. So density equals molar mass times pressure over R times T. That's this formula here. If I were looking for molar mass, I might use this form of it. If I'm looking for density, if I know them both, I'll use this form. Otherwise, you can just use one and solve for what you need. And we want to compare the density at 0 Celsius and 380 torr of carbon dioxide compared to its density, same gas, at STP. So remember that STP is hiding a standard temperature, which would be 0 Celsius, and a standard pressure, which in torr would be 760, right? So this is 2 separate questions here so that we can make this density comparison. And we can kind of look and see what's happening. The molar mass of carbon dioxide is 44.01 grams per mole. I found that off the periodic table. So let's find this first at conditions, the first conditions. So the molar mass, 44.01 grams per mole. And the pressure was 380 torr divided by R. Since it's torr, I'm going to use 62.0 So you have 3 sig figs. 62.4 liters torr per moles Kelvin. And the temperature, 0 Celsius, is the same as 273 Kelvin. And I found that the density in this case is 0.982 grams per liter. And if you're not sure about those units, you can always come back in and cancel out what you know cancels. So I see torr and kelvins cancel and moles cancel, leaving me grams per liter. Okay, so that would be under the first set of conditions. Under the second set of conditions, we're going to do the same thing. And this would be molar mass again. It didn't change. 44.01 because it's the same gas, grams per mole. And the pressure now is standard pressure because we're at STP. So this would be 760 torr, and that's an unlimited number of significant figures. Don't worry about that. R can be the same number, 62.4 liters torr per moles Kelvin. And now we're at STP, so our temperature stays at 273 Kelvin, 0 Celsius. So notice that the only thing different in here is the pressure, which means the volume had to have changed. There's no other way to deal with this. So if you can picture what's happening, the pressure has gone up, which means that the volume is inversely related and should have gotten smaller. And if you take a gas and squeeze it together, it would get more dense. So let's calculate this and find what we get. And we get 1.96 grams per liter. I want you to notice something, that in this case, we can see that the density increased by a factor of 2 from 380 to 760. That the pressure increased by a factor of 2 from 380 to 760 torr. And since everything else was identical, then the density also increased by a factor of 2 from 0.982 to 1.96 grams per liter. So that gives you a little bit of a way of looking at that differently. You can always use the theory of that if you need to, right? Since the only thing that changed was the pressure. All right, finally, one more example. This one uses the mole fraction version of Dalton's law. So let's see what we got here. They tell us that we're going to take a mixture of noble gases and use them as blanketing gases to stop other chemicals from reacting, to keep air from reaching them. So we're going to use our mixture of gases. That's 5.50 grams. Be really careful. We need mole fraction, not gram fraction. So we're going to have to convert these. So this will be 5.50 grams of helium and 15.0 grams of neon and 35.0 grams of krypton. And he put them in a container at STP. So remember that this would be standard temperature and pressure, so 0 Celsius and 273 Kelvin. Okay, so if we're going to use the mole fraction, we could do Pivnert multiple times. Notice that, or Pivmgert in this case, and we could come in and we could say Pivmgert, and then we could solve for P, which would be GRT over VM, and the grams would be the mass that we were given, and we can pick whatever pressure we want. So, standard pressure, which would be, I'm going to choose atmospheres. I like it better, right? So I could plug that in, and I could plug in the volume of the container, except that I don't know that. So I can't do it this way, right? So this is something that you do as you're thinking about gases, as you go, oh, this won't work. I need to find a new way to do this. So we'll come back in and use the mole fraction way. So we'll convert grams of helium to moles of helium. And from the molar mass on the periodic table, that would be 5.5 divided by 4 gives me 1.375. I'm going to keep long sig figs right now. Moles of helium. I'm going to do the same with neon. 1 mole of neon and 20.18 grams of neon. I hardly ever use that one. I don't know it. Gives me 0.7433 moles of neon. I'm going to do the same thing with the krypton. I definitely don't know this. So 1 mole of krypton is 83 point, 0.8 grams. And I find that this is 0.4177 moles of krypton. So now I have moles of all these three gases in this container, so I can come and add them up, right? So when I add them up, I get a total of, plus equals, a total of 2.536 moles total. So since I know that the standard pressure is 1 atmosphere, I know that this has to be the total pressure of this mixture. All right, they told me that this mixture has a pressure that equals standard pressure. So this is my total pressure. So remember that we're going to do P of my partial pressure of my gas. So in this case, the partial pressure of helium would equal the mole fraction of helium times the total pressure. So this means that we need to find the mole fraction. So to find the mole fraction, we come back in and we're going to divide each gas by the total. So 2.536, 2.536, 2.536, and this gives me mole fractions of, I didn't even figure it out, 0.542, and this is my mole fraction, and this one would be 0.293, and this one would be 0.165, and those are my mole fractions, equals the mole fraction of helium, equals the mole fraction of neon, and equals the mole fraction of krypton. So now I can do these times my total pressure, and in this case, my total pressure is 1 atmosphere, so the pressure of helium equals the mole fraction, which would be 0.542, times the total pressure, which is 1 atmosphere, and it's the same thing, 0.542 atmospheres. So basically, if this wasn't 1 atmosphere, then we'd have to do all that multiplication. But what we can do now is say that because the total pressure is 1 atmosphere, I can come make these atmospheres, and I know my pressures. So hopefully this was helpful for you to see some different examples. We're going to work really hard on this in class so that you have lots of examples to look at. So let me know what questions you have, and we